All right, this is lecture 2 on fog studies. And I think of this lecture as the fog catcher lecture. Almost rhymes. So we talked in the first lecture about what fog is. It's tiny little particles that are floating in the air, essentially. And for some types of fog, we didn't really talk about the different types of fog. We'll get into that more. But for some types of fog, they tend to be accompanied by wind, particularly what is known as advective fog, which occurs near coastlines like the California coast or the west coast of the US or South America as well. The type of fog that is advective fog is blown by the wind, typically forms over the ocean, blown over onto the land during the night or late afternoon, and there it remains for a while, but the wind causes it to be blown, and that is, for the purpose of fog capture, useful because it moves the moisture. So when the moisture encounters some sort of a vertical structure here, some of these little droplets will then accumulate on the vertical structure. And then if enough of them start to accumulate, the droplets on the structure get bigger, and then the water drips down. And that's essentially how a fog catcher works. There are types of fog. For instance, there's another type of fog called radiation fog, where the fog is typically not associated with wind. It's typically in very still conditions. And in that case, it's likely that less of the fog droplets will hit on surfaces. Some of them still will, but less of them than for advective fog or coastal fog. So typically the advective or coastal fog. Another type of fog that is associated with wind often is orographic fog, where you have a mountain and the air that's blowing this way gets blocked by the mountain, goes up. And when air rises, pressure is lower here. So even without any exchange of heat, processes that don't involve exchange of heat are called adiabatic processes. Without any heat exchange, what happens is the moisture that's in the that's in the air, as it rises, without any heat exchange, the air cools, which is something I find fascinating. That's why often when you go to the top of a mountain, it's cooler than when you're on the ground. That is because as the air, as you get higher, the air experiences a lower pressure. There's less air on top of it when you have a big difference in elevation between the top of the mountain and another part of the mountain. And then when there's that big difference in elevation, there's lower pressure up here as you get higher. When there's lower pressure, I think of it as kind of you're taking the lid off a pressure cooker. You have all of this water that's in here, in the air, that isn't being pushed into the air by the pressure. It's easier for the water to come out. In other words, the air at that lower pressure, it gets cooler and it can't hold as much water. Those are the two things that happen. It gets cooler up there, and cooler air can't hold as much water as warmer air can. It's the water that's in the air, water vapor, and all air, most air, has at least a tiny bit of water vapor. Some has more than others. But under lower pressure, you have a lower temperature. So air that was warmer, as it rises, it cools down, and it tends to release moisture. If it's anywhere close to having a high humidity or even a medium humidity somewhere here, comes up here, it's going to have a much higher relative humidity for the same amount of moisture. And it's going to reach the point where that moisture has to come out of the air. And so you're going to tend to get fog and clouds over mountains. That's why you tend to see, if you see a mountain range, there'll often be clouds that are draping in the mountain at the mountain peaks. To the mountain, somebody on the mountain, that would be fog. All right, so that's called orographic fog. It's formed by mountains, basically. Orographic talks about, it refers to the height difference associated with mountains and the structures associated with mountains. Okay, so sometimes you get a combination of advective and orographic fog. So if you have a water here, for instance, like in Chile's, if you've ever been there, there's the ocean here, and then there's the coast, and then you immediately get mountain ranges there. And so you'll have mountains that are a couple thousand feet above sea level. You have that in California too, but you have it much more in Chile, and there's a lot of it. It's a really long coastline, even longer than California's. But they're very similar in some regards, that they're often thought of as mirror images of each other. But where you have these mountains right near the coast, you can get the advective fog, and then it rises here, and so you might have a little fog here, but you have a lot more up here as a result of this lifting of the air due to the mountain. So these are often good locations for trying to do fog water collection. Mountaintops, particularly if they're close to the coast, but not even necessarily. You don't have to do. You can still get fog in inland areas if you have these mountainous regions. So, how do we collect fog? Well, for the past, I would say, since the 1960s, particularly in Chile, technologies have been developed that utilize some sort of a mesh. And what the mesh is, it's basically ribbons, threads. It's typically made of polypropylene. It's actually not polypropylene. Or maybe actually it is polypropylene. I always get my plastics confused. I know that most of them aren't good, but they have their purposes. I get concerned when I see them lying around, single-use plastics, but that's a whole other story. But these mesh are made out of polypropylene, plastic material. And what happens is little water droplets that are in the air, the fog, as it's blowing through the mesh, those droplets, some of them get captured by the mesh material. And for the same argument I gave earlier, as they get heavier, they start dripping down the mesh, and they enter a trough or some sort of a means of collecting the water. And if the trough is at some sort of a slope, then the water will run towards one end of it. And there's usually some sort of an opening there. And then if you have a means to collect the water, a barrel, or in my case, a rain gauge, something that can measure the water as it's coming down, and you support this whole thing, here's your fog collector. And a fog collector is really supposed to represent or mimic a tree, because this is what a tree does. A tree that's in the fog zone is going to have leaves or needles whose structures are designed through evolution to capture the fog water, which then drips down onto the roots of the tree. Or in some cases, some trees actually can absorb some of that water through their stomata. And it also reduces the amount of evapotranspiration that the trees undergo usually. So through whatever means, the water that accumulates here on tree leaves or needles helps the tree. It provides moisture for the tree through one way or another, whether it's conserving moisture that it would otherwise gather from the ground, or whether the water drips down and is then providing moisture at the roots of the trees, or whether the water is absorbed by the stomata themselves and enters the trees through that path. So what we're doing is we're building fog collectors like this. They're known as standard fog collectors, and the paper I posted for this week by Schemenauer et al. Talks about the design of a standard fog collector. So I'll mention his name here. He was he's still alive. He's a pioneer of fog collection. He was the person who actually I contacted when I was interested in it back in 2004. And he started a nonprofit called FogQuest, whose goal was to deploy fog collectors in places that needed water that fog might be able to provide. And he's deployed it. He and his nonprofit have deployed fog collectors in dozens of places around the world in many countries: Chile, Eritrea, Israel, Morocco, many places. They're not the only one. There's other people who we can talk about who are deploying fog collectors in different places too. But this was the first, I would say, concerted, as far as I know, one of the first concerted international organizations to do so. And of course, fog collection happened long before the 1960s, but that's the first time, at least that I'm aware of, that we actually built devices that would do it. Earlier attempts at fog collection, or not only attempts, but successful forays into fog collection, used existing structures. I know in the Canary Islands, which is another foggy zone, they had a tree called La Hierra. I think it's called, I don't know if it's the island or the name of the tree, but this tree would collect a lot of water from fog, and people would come and get the water that would drip down from this tree, or probably from many different trees there. So, and then there's also archaeological evidence that many native peoples in South America may have lived in areas because they were prone to fog, and that was a place where they could collect fresh water. And we have archaeological evidence that freshwater collection occurred in some of these places from fog. So we're talking 10,000 years ago. So there's a lot of interesting history around our use of fog. Now it seems like a new, innovative thing. It certainly is, the fact that we build these ourselves and try to deploy them, and that they passively collect fog water. It doesn't take energy once they're deployed. You have to maintain them. But the paper that I'm going to have you read, the Schemenauer paper, I think it's a 1994 paper, talks about the design of the standard fog collector. And I'll give you a couple of the features of it here, but please read the paper and we'll talk about it next week a bit if you have questions about it. But it is the design that I build. So I'm using essentially the same thing he talked about. A couple features of this design are it's a 1 square meter, and I shouldn't just say 1, I should say 1.000, probably within a centimeter. Square meter fog collector, which means that each side of the square of the fog collector has a length of 1 meter. And that fog collector is filled with a certain type of mesh. And Schemenauer talks about a certain type which he considers the international standard. You'll see it in the paper he talks about. And it is a Rochelle mesh. It's 35% shade coefficient. You may ask, what does that mean? It means that if you had a single layer of this mesh here, that 35% of the area of this 1 square meter is covered by mesh. So it's 35% shading. Kind of makes sense. But what Schemenauer does is he uses a double layer of it because he did a lot of experiments, so he uses 2 layers of it. So a double layer of it in the standard design. Now I have tightened probably over 100 of these and mounted mesh onto this. I can't tell you how many times I've done it. And you can vary how tight you make it. I like to make them pretty tight, but there's tightness can be pretty tight, there's a lot of room for creative expression in that. So, but I don't like saggy mesh for a lot of reasons. So I tend to make them fairly tight. And so when we say a standard, that implies a certain level of tightness, and I can't say there is one, and nor can he. So the idea behind what is standard and what's the variability between 2 identical mesh, if they were just, identical, maybe one's a little bit tighter than another, are they still going to be standard? Is one more standard than another? And there isn't really a value for that. But in him having seen my mesh, one time he said, you need to make it tighter, and I agree. And I made it tighter, and now all of my mesh are quite tight. They're fairly taut for a variety of reasons. One of which is if the mesh is loose and wind blows it, the motion of the mesh is going to cause the droplets to fly further. It's going to they're going to be little projectiles catapulted off the mesh. So we make it tighter to try to prevent that from happening as much. So that's one reason why we prefer tight mesh. Also looks better. It looks sloppy if it's not tight in my mind, but that's just me. And those are a couple reasons right there that I'll mention. Other things about his design, he wants the trough to be 6 inches wide here. We'll talk about that. We can actually make some measurements about that. The reasoning behind that is there is going to be wind pushing these droplets this way. And if this trough is too narrow, then more of the droplets are going to miss the trough and not be captured. Of course, the question is 6 inches really even enough? So I'm not sure what the history is behind that. You can read that in the paper why 6 inches was picked. I'm not sure he really says. I think he just says 6 inches is what it is. But we have measurements to show we're going to probably be losing some of that water. And that's something that we'll be able to talk about as well with some of the measurements I've made using other devices in addition to the standard fog collectors. Beyond that, the standard fog collectors are supposed to be mounted on poles. So if the fog collector is like this, that's 1 meter, of course. That's 1 meter. And the height of the poles is 2 meters. So they stand 3 meters off the ground, and a meter's a little over 3 feet. So this here is 9 feet. So they're pretty tall. The ones behind the library are even taller than that. At least the mesh amount is. I have them start lower. They're actually probably about the same height, but the ones behind the library are, they're not standard. They're more than standard. They're bigger for reasons I can talk about. One of them being that provides more protection from wind to the oak trees that they were trying to help. So that's why I made the mesh extend further down. Plus, with there's more mesh, there'll probably be more water collected. All right, and I think that's most of what I'll mention on the design right now. We'll talk more about it. A lot of the work that we'll be doing is going to be about looking at the data from these standard fog collectors, of which I've mentioned. I have deployed, I don't know how many dozens I've deployed, hundreds maybe, of these things around the state. They're not all up. Not everyone I've deployed is up, but they often need to be fixed or repaired if they fall. Sometimes they fall. I have guy wires that support them. You'll see that on the various sites. I also have a rain gauge here that measures, as I mentioned, measures the water that comes into them. I have bird spikes here to keep birds from roosting on them. And sometimes it works and sometimes it doesn't. Birds can figure out ways to push them and still roost here and leave their treasures for me in here, which you'll see and we'll talk about when we're out in the field as well. But I wanted to give you that background on the standard fog collectors and start talking next week about the data that is collected by them, because it, to me, is the bread and butter of the research you'll be doing. And I want to get you familiar with the data sets, how they're collected, how to analyze them, and how to prepare them to be analyzed. That'll be a big part of what you do this semester. Okay, we'll talk soon on Zoom. Bye-bye.